Good afternoon, everybody. Today, we're glad to have with us Professor Igor Shovkovy. Igor is very well known from all of you and very well known in the field. He's an expert in theoretical nuclear physics, heavy ion physics, high energy physics in general, and also condensed matter physics. So a very brief introduction about his career. So he got his PhD in theoretical physics from the Bogolyubov Institute of Theoretical Physics in Kiev, Ukraine, in 1997. Then from 1997 to 2004, he got a few postdoc positions in the University of Cincinnati, University of Minnesota in the US, and also at Goethe University, Frankfurt in Germany. And then he became a junior fellow at FIAS in Frankfurt from 2004 to 2006. Later on, he became an assistant professor at Western Illinois University from 2006 to 2008. And in 2008, he joined Arizona State University, where he is now. So first as an assistant professor, then associate professor, then full professor. And currently, he's the faculty head of Polytechnic Science and Mathematics of this university. Igor Shovkovy has published over 150 publications among articles, reviews, book chapters, and he has over 8,000 citations for all this work. We're glad to have him here today talking to us about his recent work. So please, Igor, go ahead.
Thank you. Thank you, Anna, for a very nice introduction. I'm very glad to see all of you here and very glad to present this work. This is work that we've done together with Jorge. Here he was an exchange graduate student for 2 months, and it was very nice collaboration, so I'm very glad to report this work. It's a little technical, so if you have any questions or interruptions, please feel free to stop me at any time, and I will be more than glad to answer the questions. I'll start with a brief motivation for this study. It's actually kind of an interesting topic, although somewhat abstract topic, because we do not have that many scalar bosons in nature. Of course, we do have many different places where we will find magnetized plasma, and of course they appear all the way through cosmology, astrophysics, heavy ion collisions, even in topological semimetals where you could have quasi-relativistic particles. Some of these ideas might be relevant. So we do have a lot of different places where magnetized plasma exists, relativistic magnetized plasma, and of course it's interesting to study their properties. Over the last few years, I was deeply involved in trying to understand the emission of photons and dileptons from magnetized QGP, and some of those references I'm pointing here. We do know from these recent studies that the emission is highly anisotropic. There are some enhancements that you could see due to the presence of magnetic field, and there are many other subtle effects that might be interesting to know when trying to understand heavy ion collisions. In this study, I will be talking about the production of neutral scalar bosons, and this is really right now could be seen as a theoretical exercise. First of all, of course, it offers some insight into real physics because it will allow you to compare the results with those for the photons and dileptons, and for example, extract some information about the spin effects, because photons will be spin 1 particles and neutral scalar bosons will be spin 0 particles, so that has effect on the anisotropy of the emission. It may also be applicable to, for example, the emission or production of sigma bosons in quark-gluon plasma. It's a long shot to tell you honestly, so I'm not sure how realistic this application might be. But there are also potential applications in cosmology and astrophysics. There are some models of warm magnetic inflation, for example, where these ideas might be relevant, and it can apply potentially to some types of dark matter. So that's the general motivation that I have. I'm not going to go into any additional details unless there are some specific questions. So let me start with the model that we were considering. And this is the picture of a specific profile of the production of neutral scalar bosons for a specific type of magnetic field, and it shows the anisotropy of that kind of emission. So the model we are going to consider is this very simple model where there are two fields. One of them is the fermions, denoted by psi, and they carry the charge q, so it's a charged field. And the other field is the scalar bosons phi. They are neutral, so basically the interaction is given by the U-cover type of interactions. The bosons are considered to be massive with a mass capital M. The fermions have, the mass little m. When we are considering the interaction of these fermions with the magnetic field, of course, we introduce that interaction via the standard covariant derivative, capital D here, introduced in the standard way. And in the presence of a constant magnetic field, we are using this asymmetric Landau gauge for describing the gauge field, the background gauge field. Without going into derivations, you could relatively easily figure out that the scalar boson production from a plasma will be given by this very simple expression for the differential production rate. It includes, it is primarily given in terms of the imaginary part of the self-energy of the scalar field. Some notations here are kind of obvious. The boson distribution function, the energy of the scalar bosons will be denoted by capital omega. It's not E for the notation of the energy because there could be other quantities that I want to use that notation for. So just keep in mind that capital omega is the energy of the scalar bosons. The imaginary part of the self-energy also determines the boson decay rate. So if it wasn't in the plasma, but if it were in the vacuum, this might be the more important quantity. It is primarily this quantity that appears in those cosmological applications, but one way or the other, it's essentially related because inside of plasma, we have in equilibrium or near equilibrium, we will have the detailed balance, which means that the decay and the production of the scalar bosons are related to each other. Their rate will be the same actually, so it shouldn't be surprising that this decay rate is also determining the production rate in the plasma. When we are considering the production rate, of course, we will consider the bosons to be on the mass shell, and they will satisfy this standard dispersion relation. A few words about the fermion propagator. Everybody in this audience probably knows, but just to make sure that we're on the same page, the propagator is not translationally invariant because we have the translation symmetry in the plane perpendicular to the magnetic field broken by the magnetic field. Essentially, the particles with the momentum perpendicular to the magnetic field do not conserve their values of the momentum. The momentum changes as the particle is moving in a spiral. The translation invariant part, by the way, but of course, the breaking of that translation symmetry is very, very simple. It's completely done by this Schwinger phase, and the rest is the translation invariant part. And that reflects the fact that even in the magnetic field, there are so-called magnetic translations that remain a good symmetry in the problem. So the translation invariant part could be, of course, written in different ways. I will be using this kind of mixed representation where I perform the Fourier transform in the longitudinal momenta, and by that I mean the P0 and P3, or the momentum along the magnetic field, and the time-like component, so the energy. Of course, the partial translation Lorentz symmetry remains in that 1 plus 1 dimensional space. The perpendicular direction is, of course, special. This mixed representation allows you a very simple form of the fermion propagator where the poles are well defined because essentially it's only this longitudinal part of the momentum that appears in this denominator, and the numerator is given in terms of Laguerre polynomials denoted by L sub n. So nothing super special about this, as it's well known, and I'll just remind you here what we are using. The self-energy can be written in a very simple form only in terms of the translation invariant part of the propagator. Of course, this is the consequence of using the lowest order approximation where I'm considering the self-energy at one loop order. Beyond the one loop order, this will be much more complicated. In fact, the Schwinger phase will play the role when you go beyond this approximation. In this sense, I could use the momentum representation for the scalar self-energy, and k is an actual momentum, which is conserved for the scalar particles. Remember that they are neutral particles, so the momenta in all the directions are conserved momenta. However, it mixes kind of more complicated with the momenta and the representation of the fermions in this mixed representation. Now, this is the self-energy itself. For the production, we need the imaginary part. So formally, that corresponds to cutting this diagram. We don't do it right away. In fact, we will consider this automatically appearing as a cut when we are going to extract the imaginary part from the actual diagram. And that will be relatively straightforward exercise. If you cut the diagram, you will appreciate that potentially there are all three processes of this type that contribute to the production of scalar bosons, provided we have this energy conservation condition satisfied. And there are different signs for this lambda and eta representing different processes. For example, when lambda is positive, it means that the energy, by the way, the energies here are positive definite by definition. So basically, that's the reason I need this eta and lambda signs plus or minus 1. When lambda is positive, for example, you would have the energies subtracting each other. So basically, it will represent the processes where either the particles transitioning from one Landau level to another, or antiparticles go from one to another level. And whether this is particles or antiparticles will be controlled by this eta sign. Anyway, the interesting and kind of unusual thing about these diagrams is that if you think of the corresponding process happening in vacuum without the magnetic field, actually it doesn't have to be vacuum. What I mean by that, zero magnetic field case. In that case, you will appreciate that only one of these processes truly allowed. That's the particle-antiparticle annihilation producing a scalar boson, and the other two are completely forbidden. Without the magnetic field, that is very easy to understand why the other two are forbidden, because if you go to consider that process from the rest frame of the scalar boson, you will appreciate that you cannot possibly satisfy the energy momentum conservation. And in the presence of the magnetic field, the energy conservation is much more relaxed, and this relation can be solved. And in fact, you could find the phase space for all the three processes happening. Of course, there are certain limitations on the energy, how big it should be. It should be larger than a certain value or smaller than a certain value for different types of processes. But essentially, these are the conditions that you will see. And you could also appreciate them in the form of these transitions between the Landau levels. So the transitions that essentially correspond to a classical synchrotron emission will correspond to the transitions between the particles, between the states with the positive energy. So essentially, the synchrotron emission could be seen as the charged particle going from one Landau level to another Landau level with a smaller energy. And that comes with the emission of the particles, photons or scalar bosons. By the way, this is exactly the same relation that appears in the emission of photons. The other diagram is the same thing, but happens between the antiparticle states. So you could imagine as antiparticles moving in the opposite direction and emitting in a different direction, but essentially it's a similar process. And of course, there is a quasi-classical analog of those emissions. There is also this particle-antiparticle annihilation. Think of it as particles and antiparticles moving in different Landau orbits, annihilate each other and produce scalar boson or whatever other particle you could consider. Leaving aside all the details, you could calculate that imaginary part of the self-energy analytically and write it in the form of infinite sums over Landau levels, which is understood, of course, because those are the transitions that are happening between the particle states or antiparticle states. And you will get this seemingly rather complicated expression. I didn't write all the definitions here. You could find them in the paper if interested. But what I want to emphasize is that we used exactly the same definition for the functions that we had in the case of photon or dilepton emissions, but the expression itself is different. So it resembles the same structure, but of course the structure is different. All of these prefactors in the definitions, they are different. All of them are different, and of course they represent the fact that we have different selection rules when the transitions happen, different spin of the particles is emitted, and all of that is reflected in the structure of this expression. So similar but different, that's the bottom line. We can relatively easily consider a very special case. In fact, this was the only case studied previously in the literature. And Ricardo and company did this about 5 years ago in this paper. So I believe we have exactly the same expression, although it seemed to be written in a slightly simpler form, if I understand it right. We formally derived it in a slightly different form and then were able to reduce it to this expression. And this expression is much, much simpler, first of all. Notice that here there is only a single sum of Landau levels. There are no those complicated functions depending on the Laguerre polynomials. So there is no dependence on the transverse momentum, and that's basically where that dependence was sitting. So it's all much, much simpler. H0n is just some combination of the Fermi distribution functions. So this is indeed a very, very simple expression. Numerical calculation of this, of course, is super easy as well. Now, unlike the general case, however, this is an extremely restrictive kinematics. So kinematics is such that when you're considering the emission of the scalar bosons or the photons or whatever else you consider it with this K-perp 0, it only means the emission along the magnetic field. So basically you ignore all the information about the possible production in all the other direction except for one specific direction. And as a result, because of this extremely restrictive kinematics, there are a lot of restrictive things we see from this expression. First of all, immediately obvious that only for the energies larger than 2 m, the production will be allowed. Otherwise, it's completely forbidden. If you take any omega less than this threshold of fermion, anti-fermion production 2 m, basically it will be exactly 0. So that's first thing that we see physics-wise. Only the annihilation processes contribute to this emission in the direction of the magnetic field. All the particle splitting processes are forbidden for this restrictive kinematics. And of course, as we will see later, those particles play a very important role in the production of scalar bosons in the magnetic field. Using this expression, which is much simpler, of course, K-perp equals 0, I could also reproduce exactly the B equals 0 limit. Well, as always, when we are going to try to consider B0 limit, I will have to introduce a continuous variable 2nqb, which will be, of course, continuous because b goes to 0 and the sum n goes to infinity, and essentially it becomes a continuous variable. I could look at that expression at K-perp 0 and actually write the corresponding expression where you would see that I replace the absolute value of kz, the magnitude of kz, with the complete k vector magnitude. And the reason is very simple. When we don't have magnetic field, the Lorentz symmetry is restored. So the dependence on kz actually tells me all the dependence on any momentum in any direction. So this is that special case where just that single simple expression allows you to reproduce the complete expression. So we will get this formal expression. We could exactly integrate the expression and get the final result, which actually happens to be agreed with the exact expression at b equals 0 that you could find in the literature.
Sorry, Igor.
So that, yes.
Can I ask you something? What is
Please.
V0 in the integral?
V0 is just the limit, which is something like omega squared minus k squared minus 4m squared over 4. It's defined in the paper, but I forgot to quote it here. It's some expression similar to this square root type of, well, actually to the expression like omega squared minus k squared minus 4m squared, okay, which defines the actual limit of integration.
Over b, maybe.
Over 4, actually, because over b, yes, probably because it's unitless. No, it's not unitless. I don't think it's unitless. I don't think it's unitless, but yeah, it has some units. I just don't remember right now. Yeah, I think it has the units of energy squared.
Yeah, energy squared. Okay.
Yeah. So you could find the definition in the paper. Sorry, I didn't quote it here. So anyway, that's good because there is certain confidence that we reproduce the exact result correctly. And of course, in retrospect, of course, it's not super surprising because, as I said, this k-perp limit was already considered before in the literature, and they also verified that b equals 0 limit is correct, except that I believe in that paper temperature was 0. Ricardo could correct me if I remember it wrong. So anyway, now we have the analytical expression and we are ready to calculate the production rates. So before I go there, I would like to emphasize that there are certain interesting cases that would be impossible to consider at b equals 0 or in vacuum. So it's important to emphasize that those limits are open to us and will be interesting to consider. So obviously we will consider the supra-threshold scalar boson case when the mass of the scalar boson is larger than twice the mass of the fermions, so over the threshold of particle-antiparticle production. And of course, we know that in the zero magnetic field case, that is a legitimate calculation that can be done as well. And by the way, the previous slide, B0, it was also giving non-zero rate only in this case. However, in the presence of a magnetic field, there is a non-zero production rate even in the case when the scalar boson is less than 2m. Of course, there is absolutely no analog of that rate when b equals 0. And the reason for that is that the particle splitting processes play a very important role in this case. So that will be one of the limits that we will consider in this problem. We will consider several different choices of the parameters to get a better understanding how the effect of the temperature acts in the system, how the results change with the strength of the magnetic field. So we consider relativistic and ultra-relativistic limits. So in the first case, the temperature is comparable to the other scales, fermion mass and the bosonic mass and the magnetic field. And in the other case, it will be considerably larger. Two values of the magnetic fields, moderately strong or very strong magnetic fields. And we will sweep through a very large range of the scalar boson energies from essentially the bottom line value, capital M. Of course, we cannot produce scalar bosons with the energy less than its mass because it's on mass shell. And of course, we can push it as high as possible. On the other hand, there is, of course, technical limitation because the larger is the energy of the scalar boson, the larger number of Landau levels we need to account for when doing those sums. And in some cases, we run up to hundreds of Landau levels. And of course, that sets some limits, how large the temperature, and in this case, how large the energy should be considered. So that gives us some limitation how far we can push. But we actually have some results, maybe up to 100 am or so.
Sorry, Igor.
So this is, yes.
In the previous slide, yeah. Why is it the m smaller than 2m small, zero rate at b equals 0? Because this is the usual case, no? I mean, I don't see why.
You mean capital M less than 2m?
Less than 2m, yeah.
This one?
Yeah.
Well, simply because if you look at that rate, you will see there is this threshold set by the particle-antiparticle production. You cannot merge particle-antiparticle and create a scalar boson out of it if you have the energy less than 2m.
Okay, yeah. Okay. Yeah, it's the margin. Okay, sorry.
Well, that said, I should probably give an additional comment, which I'm not sure if maybe that was also the root of the question. In principle, this is the leading order calculation. Beyond the leading order, you could actually have 2-2-2 processes, so producing from 2 fermions 2 scalar bosons, and in principle, that has less constraining phase space, but that is a sub-leading order.
Okay.
So anyway, this is the results. These are the results for the differential production rate. So what you see here is that differential production rate D3R dk3. It's considered as a function of the angular coordinate. So theta is the angle measured from the direction of the magnetic field. Theta 0 means the emission along the magnetic field. Theta pi over 2 on the other end here is perpendicular to the magnetic field. We are not considering beyond that because essentially it will be a mirror reflection of the same rate when we go all the way to pi, because then it will be just a mirror reflection against this half pi line. So if you could look at this dependencies, one thing that immediately seems obvious that the rates at theta equals 0 at small values here are much smaller, logarithmic scales here, right? So it's much smaller typically than the rate in the direction perpendicularly to the magnetic field. So essentially, all of those rates along the direction of the magnetic field are actually very, very small compared to the emission in the direction perpendicular. And that means that all of those estimates that were considered only this special case, theta 0, equivalent to k perp equals 0, that means that they are highly underestimating the overall rate because most of the production goes in the other directions. However, of course, this rate is non-zero because we are considering over the threshold mass of this scalar boson, it's 3m, which is obviously larger than 2m, so that production is allowed even at theta equals 0. It's small, but allowed. And of course, as I said, the rates grow and the rates decrease typically with energy. Of course, the larger is the energy, the higher you have to go in the phase space or in Landau levels, and of course they will be occupied not as large, as heavily as the low energy states, and of course that tends to suppress the emission. So that's all kind of obvious. However, there are also rates that have absolutely no analog at b equals 0. And this is the rate for the sub-threshold boson, scalar boson mass. So notice I'm considering m equal little m divided by 3. So it's essentially only a third of the fermion mass. You need like, 6 different scalar bosons to reach the threshold. This would be totally forbidden if you didn't have the magnetic field. Of course, the rates at theta equals 0 totally vanish. So this is that special case that was considered k perp equals 0. Theta 0, there is absolutely no rate, it vanishes. And this goes exponentially quickly down to 0 when theta approaches 0. However, the rates are non-zero at other angles, and it's non-zero even for the energy less than the threshold of 2m. Notice that this special first line at the very top, it's non-zero rate, even though that we are considering subthreshold energy in this range. M is a third, omega is 1.5, and this is 2m. So we are in this regime, which is totally due to the magnetic field and the quantum processes involving the particle splitting processes. They dominate. In fact, they are the only ones contributed in this case. So this is the impression of the angular distribution of those production rates. So I took first 3 panels for the suprathreshold scalar mass and some specific temperature, some specific magnetic field, and just vary the energy of the bosons produced. At small energies, of course, we have relatively few processes contributing, so there are a lot of these spikes that represent the Landau-level thresholds. When we increase the energies, those spikes start to merge more and more closely together, and you get nearly smooth profile with a lot of those transition thresholds still spiking out over the average production. There are 3 different processes represented in these diagrams, and they are color-coded. The annihilation process is the red lines, the green are the particle splitting, and the blue is the total. So notice that predominantly the red one dominates over the green, which means that the annihilation processes dominate in this regime. So that's the process that allows the B0 limit. If you consider the subthreshold scalar boson mass, the picture changes somewhat, actually changes dramatically in some cases. For very small energy in that narrow window, there is only one blue line. Technically, it's all coming due to the green lines, the particle splitting processes, and the total is exactly the same as the particle splitting. There are absolutely no annihilation processes in this case possible. When you increase the energy, gradually the annihilation processes start to contribute more and more, and eventually at very large energies they may even dominate over the particle splitting processes. But in either case, those 2 processes are more or less on equal footing. So in this case, we have a lot of contributions coming from the particle splitting processes. Notice that in the direction vertically, there is almost no rate. Well, actually, there is no rate really. In this case, when M is suprathreshold, there is, of course, non-zero rate. It's small compared to everything else, but it's non-zero. It's typically non-zero, very small here, but it's non-zero. In this case, actually, it's exactly 0, and it's hard to see there, but it goes directly all the way to 0 there. Because in this case, it's truly a 0 rate in the direction along the magnetic field. And most of the rate is coming from the other directions. So the total rate will be dominated by everything else. And also notice this anisotropy, which in the language of heavy ion physics will be called positive V2. In the plane perpendicular to the magnetic field, the emission dominates. So now I could show you the integrated rate. And in view of that angular distribution, you would know that it's really dominating most of the time by the emission in other directions, not along the magnetic field direction. This is the formula I'm going to use for the integrated rate. Notice that I'm integrating over the angular coordinates. Integral over the other angle is already done. It's a factor of 2 pi because the emission does not depend on that coordinate. And there is an extra factor k here coming from essentially the phase space. Here we had d3r over dk3, and of course, after some rearrangement, some phase factor of k appeared in the formula on the right-hand side. Which basically means that for small k, the phase space is small and the overall rate will be small. By the way, it means what? This formula represents the number of the scalar bosons produced per unit time, per unit volume in the energy range between omega and omega plus d omega. So that's the meaning. And of course, for small omegas, the phase space is small and it will be going to zero because of that K factor. We will also introduce these characteristics that formally describes the anisotropy of this production. And of course, V2 is not perfect because we saw it's not kind of ellipsoidal profile, but at least quantitatively, it will tell us that the emission is mostly going perpendicularly to the magnetic field, positive V2, or along the magnetic field, negative V2. So that's just to characterize. As you could guess from the pictures I was showing, it's going to be mostly positive V2. So these are the results for the integrated rates as a function of omega. Notice that on the top diagram, which is the mass of the fermion larger than the threshold 2m, and the lower panel is less than 2m. In the suprathreshold, of course, we have the dashed dotted lines, which represent B0 limit. In the other case, that kind of limit doesn't exist at all because the rates totally vanish is in this subthreshold regime. The rates increase with the temperature. They have somewhat similar profile to the blackbody radiation, with the peak somewhere around several times the temperature. In each case, for the higher temperature, the rate is going higher. For the lower temperature, lower, color-coded. And of course, that is in both cases. And there are open symbols here, diamonds and squares, which represent the annihilation and particle splitting processes. And of course, you could see that in suprathreshold, diamonds annihilations predominantly dominate the total rate. And in the other case, the same happens, but only at very large energies. At energies up to several times the temperature value, in fact, the particle splitting processes dominate, especially at higher temperatures. And of course, that represents the fact that those processes become really very important, and they extend all the way to very small energies. The energy is only in the lower case larger than a third of little m. And there is a whole range here between a third of m and 2m where only particle splitting processes contribute, because the other ones will be simply forbidden by the energy conservation. The rates are always larger than the B equals 0 rate. Well, you don't even have to look at the lower panel because it's always was 0 rate before the magnetic field was turned on, but you could see clearly that in the upper panel, the rates are considerably higher, and it's an order of 10 higher for this magnetic field, 2m squared. It will be even larger enhancement when we go to a stronger field. And there is that non-zero rate in that special regime, which you would never find without a magnetic field. Calculation of the V2 reveals these results. The results are somewhat similar at large energies in both cases of the small and large scalar boson mass. It approaches rather large values of about 0.2 to 0.3, which of course is rather large anisotropy. The behavior at small energies is very different in the supra and subthreshold cases. In this case, in the top case, large boson mass, the V2 is highly variable. It can be even negative when it is dominated, by the way, by annihilation processes. In the other case, it's very large and positive, still varying a lot, but largely positive. And that is because of the particle splitting processes, which are completely forbidden to go in the direction along the field, and they are really pointing in the direction perpendicularly to the magnetic field. So that's the summary of the results here. And of course, the qualitative difference is really only at small energies between these two different cases. The temperature has the tendency to slightly wash away the V2. As you could see, the red line is lower, or it becomes lower at sufficiently large energies. And that is, of course, also partially understood because the particle annihilation processes which dominate at high energies, they are typically not as anisotropic as the particle splitting ones. So this is the summary of similar results for a stronger field. There is not much more here than I showed in the previous case. All the qualitative behavior remains roughly the same. The enhancement is even larger. It's kind of hard to see because I'm showing a wider range of the rates here. But if you compare the actual numbers, you will see that this rates with the larger magnetic field became even higher than before. And of course, it's additional enhancement due to the magnetic field in the presence compared to the weaker magnetic field or zero magnetic field. That's pretty much all about those results. So to summarize, what I was trying to tell you here is that in the presence of a non-zero magnetic fields, there are three relevant processes that dominate the production of those scalar bosons. In addition to the B equals zero processes, which is number 3 here, particle-antiparticle annihilation, we have two others, particle splitting processes, which involve particles or antiparticles, and in some regimes they actually dominate. It is very different, of course, from the B equals zero limit, because in that case only the annihilation process was contributing. The scalar boson emission is highly anisotropic. We call it butterfly shape in the paper, which is essentially the shape where you have very small emission going in the direction of the field and most of it into these wings of the emission. Particle splitting completely doesn't contribute at all in the direction of the magnetic field, okay, perp equals 0. This is actually something that can be again understood relatively easily from the selection rules in that case. If you consider the selection rules, you will appreciate that essentially particle splitting processes, they require transitions between different Landau levels on the one hand. On the other hand, because of the spin 0, those processes will be forbidden because they typically involve a spin 1 production as it was for the photons or dileptons. In fact, in the case of the photons and dileptons, those processes were sometimes dominated because the photons were spin 1 particles, and for the scalar bosons, they are completely forbidden in that direction because of the simple selection rule. Spin angular momentum conservation, if you wish. Production is also allowed in the present magnetic field in the subthreshold energies smaller than the fermion anti-fermion annihilation threshold, which is 2m. And of course, this is only possible when the capital M is less than 2m. And this is possible, and it might be important. In fact, in some applications, it might be really important. So that is one of the typical profiles that I was showing. It's one of those in the diagrams, and that's how it looks like. Magnetic field also highly increases scalar boson production rate. And generically, there is a certain understanding why it happens, although strictly speaking, we didn't analyze it in full depth. And the reason that enhancement is happening is due to the increase degeneracy of the Landau levels as you increase the value of the magnetic field. Essentially, each Landau level is coming out of the B equals 0 limit when you could imagine the density of the state kind of collapsing on a specific Landau level, and increasing the density of those states, especially at small energies, has the tendency of increasing the phase space proportional to the magnetic field basically, and increase the rate that way. So we know that the magnetic field will generically increase the total rate, and this might actually have very important application in that magnetic, warm magnetic inflation scenario that was partially motivating this study. And with that, I think I will stop, as this should be my last slide.
Thank you very much, Igor. So now we will open for more questions. Christian?
Thank you, Igor. Very nice talk. Um, you said that when you have a splitting only for different for magnetic field different from zero, but as far as I know, if you have finite temperature, you can also have splitting because of scattering with the thermal bath.
Uh,
Usually, it appears as
right.
proportional to 1 minus NF. Or
Right. It's actually related to what Anna asked during the talk, and I was trying to specifically emphasize that when you have this one loop diagram or essentially leading order calculation, it's completely forbidden. However, if you're going to consider the sub-leading order, basically imagine a diagram when the particle antiparticle, or if you wish, particle goes and splits off several scalar bosons in the same process. So basically this will be suppressed by additional coupling constant. That rate will be indeed allowed. So what you call the effect of the bath is essentially you need additional giving away of certain momentum or getting additional momentum. It's like comparing the ORCA and modified ORCA processes in the same sense. That one of them will be possible at the leading order because it involves only one vertex of interaction, and the other case you need to go at least to the next order.
Yeah. No, but I mean in the leading order.
In the leading order, it's completely forbidden because that's basically all there is. You cannot. This expression that I quoted is actually exact B0 result. And you could find it in the literature. At this order, this is all there is. As soon as we have omega greater than 2m, there is non-zero rate. As soon as omega less than 2m, we don't have the rate. And omega has to be larger than the scalar boson mass because we are considering on mass shell.
Yeah, maybe it's
this is the formula at this leading order. There is nothing else.
Yeah, maybe it's another diagram because
yes, it is another diagram indeed.
Leading, but the stances, for example, you have something like a scattering with the thermal baths includes some NF factor, for example. So at
well,
temperature or one
again, that will be the subleading order diagram indeed.
The subleading, okay.
Yeah.
Can I ask you another question? I mean, this slides angular dependence. Those the size of those spikes are physical or
partially yes. Partially yes. I didn't go into any of that, but we were discussing a similar issue in the case of the photon production. Essentially, at the subleading order, you will, of course, have to consider that the energy of the fermionic states in a thermalized plasma, they actually are not sharp energies, but have their own imaginary parts, which essentially leads to the fact that the Landau levels are going to be spread out over a certain range of the width, which will be more than zero. And if you introduce that width, all of these peaks, each and every one of them, will smooth out over a range the width of the fermionic states. And that means that each of those peaks will get kind of a smooth top instead of sharp spike, and it will be happening over the energies roughly of the order gamma, the width of the Landau levels. The total area below this shape will still remain almost exactly the same, but the shape will smooth out. So basically, yes, those peaks will largely go away, at least in a case of small ones where they happen over very narrow energy range, they will be almost completely gone. The bigger ones, they will remain, but will get smooth top here somewhere. If you consider a certain range, that will be almost like cut off. And it will also have a little bit of sort of a spill over on the side where it goes sharply up. So those thresholds, they will get smoother. It will not be as sharp, and it will be kind of smooth over.
Okay, I see. Okay, thanks, Igor.
Okay.
Jorge has a comment about the. Do you want to talk, Jorge, or do you want me to read it?
It's okay, yeah, because I remember like seeing with Igor that the splitting process are allowed at B0, but only in the fermion masses of the loop are different. That we see that this is what is called Landau damping, that they are possible indeed, but only for different species of fermion inside the loops.
Oh yeah, that's what I did forget to say. If you have two different fermions, it's two different masses, of course. But I don't think Christian was aiming at that particular case. So when we have two different fermions, one, for example, is having mass 5, the other is 3m, then of course there will be particle splitting processes possible. But if we have a single species of the fermions, that nothing will help. You need to go to the higher order diagram.
Okay.
That's right.
Have you finished, Christian? Can you go ahead? Okay.
Yeah. Finished.
Giorgio?
Hi, can you show the simple Lagrangian again?
Absolutely.
Yeah. It's Yukawa theory, basically.
Yes,
right?
Yukawa
It's
interaction.
the Yukawa
Yes.
interaction. Just sort of thinking out loud, is there a sort of simple way without repeating all your calculations to go from scalar mesons to pseudo-scalar mesons? I guess for a start, one has to change the interaction. The last term can not be there because it violates parity.
It's very easy to go from one to the other, but the result changes. The result changes. We didn't consider it explicitly. We roughly know what it is, but
Why
it takes.
Is it very easy? Why is it?
Well, because essentially you need to insert here gamma 5 in this loop. So the only thing that changes will be some traces, and this parenthesis will be slightly different. Okay. So it's very easy. In fact, I think maybe we should even add the appendix and add those expressions. The difficult part is actually calculating this thing. We had the formula basically right away. It took a lot of time to analyze what it is, because we, in order to have good numerical precision, we have to sum up over many Landau levels. And without a supercomputer, we did this on a laptop. It took a lot of computational time. Yeah, but maybe conceptually, it's very easy.
Even sort of numerically, the symmetry properties. Okay, thanks.
Yeah. There will be some important differences, though. There will be some important differences, because the selection rules will change. And in fact, as I said, formally it appears in just this parenthesis that look different, but physics is different.
Okay. Okay, thanks.
Okay.
Norberto?
Norberto, you are muted if you are talking.
Yeah, okay. Can you go back to slide 17?
Absolutely.
Yeah. Do you understand the structure of this blue line, the upper line? Why it has some peaks, higher peaks and smaller peaks?
Well, essentially, it just comes...
changes from one line to the other. I mean, the brown line is yellow line. I don't know. It's slightly different. I don't know.
Yes, because for different energies, when you consider the positions of Landau levels when they start to contribute or stop contributing, it changes because we have different, essentially, kinematics. So we are fixing the energy. And when we are fixing the energy, then you have to consider with the change of the direction, at which point you start crossing a specific Landau level threshold. You see the processes, they're not just vertical, they are always, maybe this diagram shows, if you fix the energy, you are basically fixing the horizontal slice between how high the one Landau level versus the other one. But then if you're going to consider different processes, these lines will be tilted in different directions depending on the theta. And of course, when you start crossing a threshold depends on the actual energy. So for each and every energy, you have to reconsider this from scratch and see exactly how that condition is satisfied. And when you go through the threshold, you get a spike because those thresholds, as typically for the thresholds, they appear in the denominator under the square root. So in some cases, you kind of have a lot of phase space before you reach a certain phase space. That's when it grows kind of continuously all the time until the threshold, and then the threshold missed and something else starts to happen. And sometimes you have a lot of those thresholds coming up. So basically, that's why we need to consider a lot of Landau levels to make sure we didn't miss any of those thresholds. And that's how they appear. And of course, the larger is the energy, the more and more of those thresholds appear basically almost anywhere, because you will always find some new threshold appearing between very distantly separated Landau levels.
May I have another question? Yeah. Could you perform the same calculation using Schwinger version instead of Landau-level?
Probably, but it's going to be really hard. Extracting the imaginary part from the Schwinger method is not impossible, but much more difficult. Especially when you have a finite temperature. When you have finite temperature, you have to perform the sum, and of course that gives you some kind of elliptic functions. It's all a mess.
I wonder.
And of course,
I wonder
go
basically
ahead.
because you were saying that you have to sum over a lot of Landau levels, and when you work in Schwinger, the summation is done for you. So that's
right, and actually that's a bad thing, if you wish, in my opinion.
Okay.
The bad thing is that it's all physical processes that are happening. You have to make sure that it's this non-analyticity, if you wish, in the processes that contribute all of these threshold effects. Generically, Schwinger proper time method is good when you have sort of everything with good analytical continuation. Let me put it this way.
Okay.
If something is actually a bad analytical continuation and those thresholds is actually a specific thing where the analytical continuation is tricky.
Yeah, I can see that. Thank you.
So we had to make sure we will get the retarded self-energy, and therefore we had to make sure that it's proper analytical continuation of the expression.
Thank you.
Sorry, there was something else.
More questions?
Sorry, Norbert, I'm not sure if I answered because I think there was something else.
I thank you for sure.
Schwinger would be non-perturbative. I mean, it would still be perturbative in the coupling constant between phi and psi, between phi and the fermions, right?
Yes, but it's not about perturbative, non-perturbative. It's about analytical continuation in energy, because you need to extract the retarded self-energy, and that analytical continuation is the tricky part in the Schwinger method. By the way, I don't think it's impossible. In fact, Norberto, it's a very, very interesting exercise to do if possible, but I think it's very tricky. And maybe you are the one who can do something like that.
Thank you. I mean, at finite temperature, I understand that it's difficult. I don't know whether a cell temperature is easy. Okay, thank you.
I don't know.
More questions?
Can I ask another question?
Yeah.
Go ahead.
Which is the minimal magnetic field strength you need for a non-trivial or at least one forbidden process in vacuum? I mean,
basically arbitrarily small. Any arbitrarily small is enough. Of course, the rate will be strongly suppressed at very weak field. So it's all about magnitudes. You see, it's exponential sensitivity. So of course, when you take very small field, you will need to sum like zillions of Landau levels, first of all. And secondly, the rate will be small from each and every one of them, exponentially small, super small. But in principle, it's possible. I don't think there is a strict limit when it's strictly allowed or forbidden. But of course, physics-wise, you could appreciate that when you have a weak magnetic field, the violation of the momenta are kind of seen on the distance scales larger than magnetic length. So first of all, it's only very small energies, very small momenta where it will be something substantial. And secondly, even in that case, it will be strongly suppressed by the phase space.
So basically, you just need an infinitesimal amount of magnetic field to
give you infinitesimally small rate.
An imaginary part, small, but that exists.
Formally non-zero, yes.
Yeah. Okay, I see.
Ricardo.
Hi, Igor. Thanks for the talk. Very interesting results. I have a question. When you fixed your small and large magnetic fields in terms of little WAM, because you have different scales in the problem. You have mass, you have B, you have temperature. What's the hierarchy of the scales that you're using to say that 5 little WAM is a strong B? Just it's a number of Landau levels that is necessary, that is guiding you, that is a strong or small B?
Right. Actually, no. It's the relative temperature magnetic field, I think, is much more important. Generically, we are considering very strong fields in both cases. But we needed some variation at least so that it's not super strong. So 2m in energy units is sort of small compared to the temperature. And 5m squared is sort of comparable to our low temperature. So those are the scales we are comparing. Typically in almost any type of plasma you could imagine, the magnetic field energy cannot be as large as the thermal energy. And usually magnetic field is much weaker still than what we are considering for typical plasma. So we are slightly exaggerating the magnetic field in this sense. But the reason for that is to simplify the numerical calculation so that we will have to sum up fewer Landau levels. That was the only sort of practical thing. If we had like a lot of supercomputer time, I would probably want to go to much weaker field and sum up like thousands of levels. But of course, for this kind of problem, it's hardly justified. So this is mostly theoretical exercise, maybe with 1 or 2 hypothetical applications. So I don't think there was enough motivation to go into even weaker fields. But physics-wise, you cannot find any plasma anywhere, relativistic or not, where the magnetic field energy is as large as the thermal energy of the whole plasma. That will be super, super unusual. And frankly, the evolutionary or creation type of mechanism that would lead to something like that would be really something unusual. You could imagine something, of course, when you have vacuum, for example, with very strong magnetic field, and then you put some very, very low temperature plasma in that, in sort of sprinkle into that region some plasma. In that case, you might consider actually where the magnetic field energy is much stronger than the plasma thermal energy artificially created, but naturally you would hardly find any systems of that type. So it was mostly practical reasons, and the practical reason is the thermal energy versus the magnetic field energy. The fermion mass here is really of little importance. So basically, it's just something to give you a reference, and then everything else we're trying to compare.
What's the criteria to differentiate relativistic for ultra-relativistic plasma in the end of the day? What's the criteria that you...
Temperature versus the fermion mass, I guess.
Okay.
Yeah. because essentially that's the dispersion relation of the fermions that determines that that plasma is ultra-relativistic, temperature much higher than M or comparable.
Okay. When which kind of language you are programming to build these butterfly profiles and it's
Mathematica.
Mathematica?
This is Mathematica. This is all done with Mathematica. Most of the calculation, I would say, what is it? Jorge, correct me. Maybe 80% Jorge did on 2 laptops running basically on the same desk in parallel, and maybe one of those cases 2 I did on my laptop. So M equal 4, magnetic field 4 and scalar mass 3M. I think those mostly my data. Everything else is mostly Jorge's data.
Nice. Thank you.
More questions? I have a final question, I think, to be quick. So am I mistaken, or you said that for the integrated production, okay, Georgia said I had to go, we have all the participants had to go too. But that the integrated production, you have a maximum for a certain energy.
Yes.
Yes. So can I,
yes.
I mean,
Here. Go ahead.
No, because this cannot be an observable because you don't have production of this kind of particle in heavy ion collisions. But I mean, based on your, I don't know, previous work, or based on the similarities of these with Compton effect, can you say if it can happen also for Compton effect? I mean, in this, could it be an observable for the Compton effect, for photons produced from Compton effect?
I'm not sure why you call it Compton effect. Let me first clarify that. Basically, Compton involves photons.
Photons. Yeah.
So for the photons, it's the same thing. For the photons, it will be the same thing.
So it's
yes.
You have
it will be the same thing
for certain value energy.
Yes, it will be indeed. Basically, it's the zero magnetic field limit is just the black body radiation. When you include the magnetic field, essentially you modify that kind of black body radiation to something else, but it still remains kind of similar in some sense, that you would still have a peak somewhere at certain energies, and of course at very large energies it must go to zero. It's not obvious that at small energies it has to go to zero as well, but generically it has to, because of the phase space at least.
I see.
For small momenta, you would have small phase space, and of course then you may also consider that it goes to zero. But again, it's sort of just almost like natural thing, and it's almost natural because with a certain temperature plasma, you have certain Landau levels occupied and nothing else. And of course, that basically restricts the phase space on both ends. And it means that if we reach the optimal use of this phase space, there will be the largest production. And the optimal means the omega comparable to that temperature, roughly speaking. If you go to very small or very large, this optimal condition that everything is maximally occupied and maximum phase space to make a transition kind of starts to break down. So I think it's on general principles you expect that they should be true, but where the peak appears depends on the details.
But can it be an observable for, I mean, to say if certain photons were produced from Compton effect in the presence of magnetic field? So I mean,
yes,
if you can see this peak and how it changed with energy, then you can estimate, I don't know, if your field is increasing or decreasing, and it could be observable for this specific process.
Right, absolutely. We did not work out a specific dependence of this peak on the magnetic field. So of course that would require to consider many different cases of magnetic field and then to try to tabulate or somehow extract that information. We know that it is there, but the actual dependence have not been analyzed in this study or in the previous one on the photons. It seemed to us in the previous study about the photons that the overall change of the rate might be more representative thing, and the overall profile change, V2 essentially, V4, V6, and those things, they could be more dramatic sort of features to extract the value of magnetic field. But you are absolutely right. The peak will also potentially change with the magnetic field, and that has not been studied in detail.
Okay, no, that's very interesting. Okay, so thank you. More questions? No, if not, let's thank Igor again for the very nice seminar.
Thank you all. Thank you for being here.
Okay, I will stop recording now.